All right, guys, welcome to class. Last week, not last week, that should be day before yesterday. On Monday, we looked at your simple harmonic motion. We introduced the different cases, the mass on the spring, and simple pendulum. The other examples of simple harmonic motion, but then we focus on case one and case two, respectively. Now, there are some derivations we did, which are very, very key. We said that acceleration is directly proportional to displacement, right? The higher you displace it, the higher the acceleration. All of these things are the concepts that we looked at the last time in our lessons, right? So I say if I pull this very mass, then the more I pull it, the more it dangles, And I said that this acceleration is always in opposite direction to the displacement, and they are directly proportional. So the higher the displacement, the higher the acceleration. So that's what we looked at last week. And I have to give us a formula that relates the both of them for your simple harmonic motion. We say that acceleration is equal to this is the angular velocity and this is the displacement. We went ahead to look at the different terms of simple harmonic motion. We said that we have what we call the period t, right? And the period t is simply the time taken for a body to complete one oscillation or one revolution, right? So you can call it one oscillation or one revolution. Now it's simply time taken, right? How do you calculate the period? That's time taken to complete one oscillation. Now, time taken for the entire oscillation divided by the number of oscillation will give you the period, because the period is simply the time taken to complete one revolution, just one revolution. So this time is the time taken for the entire revolution, then divided by the number of revolutions. So hope you get the difference between period and this time here, small t. So capital T is just for one revolution. This one is for the entire revolution that occurs during that number of oscillations. And it is also measured in seconds. We looked at frequency, which has to do with the number of oscillations made in a second. You can call it number of oscillation, number of revolution. So then this thing is the number of oscillation, right? This is now the total time, at the time at which everything was happened. And I said that the reciprocal of it is going to give us the frequency. Now we looked at amplitude, which is the maximum displacement of a body undergoing simple harmonic motion. And based on this diagram, I actually told us that from this diagram, that the maximum displacement is going to be that point where the point you stretch it down to, that will be your maximum displacement, and that's your amplitude. I looked at angular velocity, which is a concept that comes from your circular motion, right? So in straight line motion, we have linear velocity. In circular motion, you have angular velocity. And angular velocity is simply angular displacement over time and is always measured in radians. But once you complete one revolution, which means this is the tiny link between your circular motion and your oscillatory motion, because circular motion is different from oscillatory motion. It's very important that we take note of that. So this is the formula for circular motion. But when it comes to oscillatory motion, right, something happens, or your simple harmonic motion, theta changes to 2 pi because that's the time taken to complete one revolution. Does it make sense now? So the formula is going to change. If I'm talking about circular motion, then I'm going to make use of this. But when I start talking about oscillatory motion, which your simple harmonic motion happens to be an oscillatory motion, then the angular velocity is going to change to what we have here, to 2 pi all over t, where t is the period. That's the time taken to complete one revolution or one oscillation. So take note of the difference between the angular velocity when you are dealing with circular motion and the angular velocity when you are dealing with simple harmonic motion. If you are still with me at this point and all of these things I'm saying again is making sense, or should I just go straight to the solving? Do you think this recap is helping you? If it's helping you, can give me a thumbs up. Okay. All right. Okay, beautiful. Beautiful. So we have your angular velocity to be 2 pi over t, right? Some persons are not on the call. Rachel is not here. Nikki Gold Silver is not here. Who again is not in class? Benita is not in class. For the ladies, check out for those that were not in class today. I don't think Ferrami is on the call. So the ladies, please go ahead and check for the ladies. I think we have more of the ladies missing classes. I don't know what the challenge might be. Um, Confidence, the person you referred is not coming to class. That is Shedrack Moto, right? So let's continue. Now, we said that this is your angular velocity as in terms of your what? Oscillatory motion. Now, I said recall that F is equal to 1 over T. So therefore, this one is your angular velocity with respect to the period. And then you could see what will happen right here when we bring in our frequency. All of these things are very important. As we start solving questions, you're going to see right here. So when you bring in the frequency, based on that formula, you have that angular velocity is 2 pi f. Now, another concept is the angular velocity for a mass on a spring. So this is the formula for the angular velocity for a mass on a spring. But then sometimes you barely see questions that has to do with angular velocity relating to the mass of a spring. It is always in terms of the period and the spring, period and these constants and these variables, period and these variables for that guy, you know. So we went ahead to actually look at also the angular velocity for a simple pendulum. But like I said, the key thing they normally ask you of is the period of the both cases. The period of the both cases. So now, and for us to get the period of mass on a spring, I had to take you through an acrobatics, and I said that this is what you need to remember. Then I gave us an assignment to go and check out for the period for simple pendulum. And that is exactly what I'm going to do right here. Then I'll give you a summary of formulas that we need to remember at every point in time, as long as simple harmonic motion is concerned. If you're still with me to this point, can you give us a thumbs up so that we can continue right here? So that let's look at well done. Let's look at period of, we'll look at mass on a spring. Let's look at the period of a simple pendulum. If you can remember, when we introduced our simple pendulum, we said that for your simple pendulum, that the angular velocity W is equal to what? The square root of what? These are the variables. I said you should prove this thing the last time. I know a good number of you did that. Why some persons did not do that? Right. So, but remember something. I'm trying to link it to simple pendulum. These are formulas by now. You should know them. That omega is equal to 2 pi all over T. So let me call this equation star. And let me call this equation star star. All right. So now we're going to substitute like sub equation star star into star. I know some of you that drink alcohol, your mind is going somewhere now. But the Lord will deliver you. So you have the next. When you plug in the next one, then you plug in the next one, you have W is 2 pi all over T is equal to, you have G over L. But remember that your goal is to get your period, right? So I'm going to move it to the other side of the equation and then divide both sides by 2 pi. So we'll have 2 pi is equal to T square root of G all over L. Sorry, what I said initially was wrong. I should divide by both sides by this. So I'm going to divide both sides. Remember, nobody's asking you to prove these things. Divide both sides. I just want to, for some of us that are very good mathematically, just is your advantage. People that are good in math is your advantage. That when you forget the formula, you can easily derive it because you know where it is coming from. But if you know that you're not good at maths, please just cram it. Nobody will tell you to prove it. So you have 2 pi divided by root G over L is equal to T. Remember, when you are dividing, it's going to be inverted. So that will give us that T is equal to 2 pi multiplied by L. Hope I'm doing the right thing, guys. Yeah, L over G. Yes. Should L be up times by L over G? Yes, L over G. That said, if you know you got this thing I'm doing now, like you solved it, can you give me a thumbs up? If you actually tried doing something around it. Okay, Meso, you did. All right. Well done. Well done. I'm proud of you. One sachet of water for you. Just go to the nearest shop, tell them I sent you, pay for it, and then collect it.
I don't drink pure water.
What do you drink then?
Ever,
Bottle water. Big woman. Oshi,
it's not about big women. I'm not feeling fine.
you're not feeling fine.
Mhm.
Oh boy. Hmm. When I grow up, I will be like you. So I'll not feel fine. I'm then drink the,
Don't
you
be
know.
like me. Oh.
Now even to feel fine, oh.
You said?
Let them feel fine, I beg. What's happening now is too much.
As in, my brother, it's a lot. It's a lot, actually. It's a lot. It's not easy. I know it's the stress and everything. You'll be fine, okay? You'll be fine. Anointing is praying for you. Or anointed, rather, is praying for you. And they also have Apostle Paul in our midst. So they are complete. All right. So your healing is sure. Yeah. Then this is my final equation, right? And let me call it equation number. This is equation 9. This is equation 10. But don't worry about all those equation 10, equation 9. This is the period for mass on the spring. And then this one happens to be the period for, what do you call it? For your simple pendulum. Is that also? Period for simple pendulum. The other concept I have to introduce, but I think if I keep introducing concepts, you guys will not be able to follow through. So as I'm solving questions, if there's anything I missed, then I'm going to bring that in. Is that okay? Maybe as the course of solving the questions, if there's a concept I didn't introduce, that question will not help me bring it in. So I think at this point, enough of the equations and everything. So what are key things I want you to always remember, my people? Now, what I want you to always remember, for example, is that your period T is simply the time, right, all over the number of revolutions or oscillations. That's in summary. That is what I want you to remember, right? So always these are your formula bank, you know. So in summary, remember that your period T, which is also measured in seconds, is equal to the time for those oscillations, all about the number of what revolutions or oscillations. I also want you to remember that frequency f is equal to the number of revolutions per second. And then for you to also remember that f is equal to 1 over what? Over t. And then for you to as well, men and brethren, remember something very important too. And what is that thing I want you to remember? It is that omega rather, is 2 pi all over t. That same omega is equal to 2 pi f. And then remember that your period t is equal to 2 pi square root of L over G. Remember that this one has to do with your what? Your pendulum. Pendulum. Then Titi is not in class. What happened? She went to her grandma again to gist her.
I'm in class.
Okay. I thought you went to gist your grandma the way you went the last time. And how is she doing? Hope she's good. So now you have M over K. Then this has to do with mass on spring. All right. So these are the key things that we have right here. And I want to say something. It's important to know that, are we together? The relationship between these two things, right? Just observe them. Right. Good. So these are the key points I want you to always remember as we walk through our journey together. Though there are more things you need to know, but for now, just wrap your head around these ones. Is that okay? Just wrap your head around these ones. Now, that said, let's get our hands dirty. Please, everybody pay attention. Hope you are following to this point. The hour has come for us to get our hands dirty. If you have any question, please ensure you ask now. Anointed, Confidence, Emmanuel, Justice, Dillian, Meso, Vicky, Good, Silver. Interesting. Good is in class today. She closed her shop to be here. That's interesting. All right. So the first question says that it's simple. A simple pendulum has a period. Are you there, guys? A simple pendulum has a period of 5.711. Can you see that? It has has a period of 5.77 seconds. When the pendulum, let me zoom in, right? I should zoom in so you can see. For some of you that has drank Gary to a point that your retina is now pleading for help. So now we have simple pendulum has a period of 5.77 seconds. When the pendulum is shortened by 3 meters, the period is 4.6 seconds. Calculate the new length of the pendulum. Now, if you observe something, this has to do with what? Your simple pendulum. And now, what are we expected to do right here? They are talking about two pendulums. Are we there now? It has to do with what? Two pendulums. Now, but what formula do we have for your pendulum? There's a formula we've established for pendulum, which we are going to be making use of right away. Now, what is that formula that we established for your simple pendulum? Sorry, guys, I'm coming. Let me rotate this. So what is that formula we've established for our simple pendulum? Now, the formula we established for your simple pendulum is that I want to now zoom out a bit so I will have space to solve that very question. I hope it's still okay here that we can still see. Is it still tiny? It's okay, right? Okay, thank you. Nikki Good Silver. All right, so this has to do with your simple pendulum, right? And for your simple pendulum, remember the formula. Don't mind the noise you're hearing. The dog no get respect. So we have that T is equal to 2 pi, this is my pi actually, then square root of what? L over G. Square root of L over G, right? So 2 pi L over G. Now, remember that this is what comes in for your simple pendulum in terms of the period. Now, remember that you are the one nobody's giving you this formula. Now, but this time around, we have how many pendulums? We have two of them. Is that not so? We have two pendulums. Now, what I didn't highlight in that formula, because I know it might be a bit heavier for us. When you have two pendulums, it means that you are relating them with a particular formula. And what's the formula you're going to use to relate two pendulums? At that point, you're going to have that T1, because their length is going to differ. The length of the simple pendulum is going to differ, but your 2 pi and your G is a constant, so they're going to cancel out. Is that not so? So I'm going to have T1 all over T2 is equal to the square root. If I have two pendulums, square root, because the lengths are going to differ, I'm going to have L1 all over L2. If you know the reason why these variables are no longer here, give me a thumbs up. If you understand why there's no longer 2 pi and G in this very equation when we took the ratio of the both of them for two pendulums, right? Because this one is a constant. This is also a constant. So they're going to cancel out. But the length differs, and that's why it's reduced to this. Does that make sense, everyone? Right. So this is the case of two pendulums. All right. So now they gave us the values. So what are the values that were given to us? One step at a time, right? Now, the first one, they gave us the period to be what? 5.77. right? So that means that my T1 is equal to what? 5.77 seconds. Now, they said something very important. Our T2, when the pendulum is shortened by, okay, has a period of this, then the next pendulum has 4.60. Remember the experiment you did back then in secondary school for some of you that went to a very good secondary school like me, that we had ACs and very wonderful classrooms, you know. So when we did the experiment back then, you have a simple pendulum bulb, the first one. Then because you are altering the length, if you can remember, they are changing the length. The longer the length, the lower the dangling. If this rope is too big, you see that as you move this guy up here, let's say you displace it to this point, and then you leave it to go up down, or it will be very fast if the rope is shorter. But when the rope is longer, what happens? The frequency is going to reduce. If you get what I'm saying, give me a thumbs up. Good. That means Titi went to a very good school. So others didn't go to the kind of school I went to. That's why they are not giving me a thumbs up. That's a problem. Now, let's go again. Titi, don't mind them. Next time they should look for the kind of school we attended. When we tell them to go to good secondary schools, they will refuse. Thank you for going to the secondary school I went to, Titi. All right. So look at what I'm saying. But I don't know whether your school fees was as expensive as my own back then. The kind of secondary, very expensive school. Very expensive. We paid 7,500 naira school fees. Very expensive. You know that kind of school that they pay that kind of school fees. You know that kind of school they pay that kind of school fees. Okay. They pay that kind of school fees you get. So that kind is the kind we attended. All right, look at what I'm saying. I'm saying that, check this. Look at this place. Look at this place. So what happens at this point? If I displace this guy to this point, right, and then I leave it, it's going to go like this, 1, 2, just that way. So the longer the rope, if this rope is very long, no matter how I displace it, because of the length, it's not going to move so much, like dangle so much. If the rope is shorter, it will dangle more. The more the frequency and the more the oscillation is going to undergo. Do you understand it now? At least those people that went to community secondary school, they are understanding it now. Okay, good. Then people that went to Greenland, is that the entity? Greenland private schools. Hope it's not the one that collapsed the other day in Lagos. There's a school that collapsed the other day. Hope it's not that one. Okay. So now we have our T1. I believe everybody is understand what I'm saying now. So we have the T1, which is 5.77 seconds. Then our T2 now, I just explained that for you to understand that the length can alter, and that length is going to affect the frequency. So this will give us what? 4.60 seconds. All right, now they said I should calculate the new length, but then when the pendulum is shortened by 3 meters, the period is 4.60. Do you see what happened here? When you shorten the length, what happens? The period decreases. Why is it decreases? Because it takes it a shorter time to complete an oscillation. That's what these figures are trying to tell you here. Those figures you are seeing, that's what it represents. That's what it's trying to tell you. Now, so our T2 is 4.60 seconds. Then T1 is 5.77. Now, I want to do some acrobatics now. It means that the new length, I pray you guys will understand this. Now, that the new length L2, according to what we have from the question, they said it does what? When the pendulum is shortened by 3 meters. Original length, the length of the first one is, let me make a statement. L1 equal to the length of the first pendulum. Let me make a statement. Length of the first pendulum. Now, my L2 at this point, they said something about the L2. They now said that it is what? Shortened by 3 meters. The second one was shortened by 3 meters, but we don't know the length of the first one. So since the second one was shortened by 3 meters, it simply means that my L2 will be equal to what? L1 minus 3. If you understand what I just did, give me a thumbs up now. Right, Richard is following. I think Richard went to a very powerful secondary school too. All right, interesting. Good. Now we have T1 over, let's now plug in our values. T1 over T2 is equal to, and what are we looking for? The question simply said we should calculate the new length of the pendulum. So we're looking for L2. That's the new length of the simple pendulum. So let's plug in our values. We have square root of L1 all over what? L2. Now we have the values of our L1, T1, right? So T1 is what? 5.77. Your T2, the period reduced, 4.60. It's equal to, I have the value of my L1. I'm using my square root. So I have my L1. L2 has changed to what? L1 minus 3. Now I have to get the value of L1 because I don't know the value of L1. So what we can do is that we can square both sides. So we can remove the square root. You understand it now? The way you solve your normal mathematics. So when we square both sides, I'm going to have 5.77 all over 4.60, then all squared is equal to, when you remove that square root, you now have L1 all over L1 minus 3. People of God, if you're following me to this point, can you give us a thumbs up? All right, beautiful. Men and brethren are following. Good, good. Now, the next thing I want to do, if you have your calculator with you, can you simply, or let me be sure that the values are correct. I don't trust some of you. So let me punch myself before you guys will give us the answer that will take us to where we don't know. So now this is 5.77, 4.60, then we square everything. So let me square all squared. That will give us 1 point. Then someone can point to see whether you have the same value. 73 is equal to L1 all over what? L1 minus 3. Is that the same thing you have with that your calculator that they use in selling provision store? Is that the same thing that we have? Hope I'm not making mistakes. Nikki Good Silver, why are you laughing? Am I not correct? 5.77 divided by 4.60, that will give me 1.254. So 1.254, let me take it gradually. 1.254 all squared will give us 1.573. Yeah, so that's the value we're going to have right there. So the next thing I'm going to do, I'm going to cross multiply. So I have over 1 here. So we have that L1 is equal to 1.5. Hope you see how I'm going gradually, right? L1 minus, I am opening the bracket. Oh, this first, so that some people will not be confused. Let me put it this way. Let me open my bracket. L1 minus 3. Now, when you open up that your bracket, my people, you're going to have that L1 will now be equal to 1.573L. L1 minus, if I multiply that figure that I have here, 3 times 1.573, you should have 4.719. Then you collect like term. You should have L1 minus 1.573 L1 is equal to negative 4.719. When you subtract that L1 minus, I know this is where people will be confused now. This is simply saying 1 minus because they have the same thing in common. 573. Without mathematics, you cannot do physics. This is minus 0.573 L1 equal to minus 4.719. Of course, negative will cancel negative. Negative cancel negative. So therefore, I'm going to obtain the value of L1. And that means that L1 will be equal to 4.719 all over what? 0.573. So the value of L1 is equal to what? So I have 4.719. In this class, you guys should be punching. That's how a class should be. I cannot be the defender, be the striker, be the goalkeeper at the same time. When I want Kimi. So this is 8.23, 3 decimal place. This is 6. Now we've obtained the value of L1, right? We have obtained the value of L1. But then what we need to get is our L2. Are we there? What we need to get is our L2. But remember that we said that L2, hope I didn't make any mistake right here. Yeah, there's no mistake. So now the value of L2, we said that L2 is equal to L1 minus 3. So that L2 will be equal to 8.236 minus 3. L2 is equal to what? So let's check. 8.236 minus 3, that will give us 5.236. Do we have that in the option? Yes, we have 5.23. So that means we have, when I divide this, L2 is equal to 5.236. A thumbs up if you follow to this point. A thumbs up if you follow to this point. A thumbs up if you follow to this point. Sorry, the women of Jerusalem in the house. Everybody is calm. Okay, the anointed is following. If you are confused, give me a thumbs down. Everybody. I know some of you are so confused at this point. Jay, thumbs down our water. Thumbs down our water. Thumbs down our water. Nikki Good Silver, did you give me a thumbs down? Or you've gone back to your business to check your customers? All right, so let's proceed. Okay, thumbs up is right there. So let's start from the very beginning. Now, we have case of two pendulums. And for the case of those two pendulums, I've said something that this formula is going to reduce to this because you have two of them. So you're going to take the ratio of the two of them. These guys are going to cancel out because this one and this one are constants. Now, because they are constants, you now have T1 over T2 equal to L1 over L2. They gave us the period of the first pendulum, period of the second pendulum. They didn't give us any information about the length of the first pendulum, but they said that the pendulum was actually shortened by what? By 3 meters. It was reduced by 3 meters. And I explained the pendulum based on the experiment, how the experiment is supposed to run, right? Then we now said that let L1 now be length of the first pendulum. Then second one, the first one was shortened by 3 to give birth to the L2. So L2 is equal to L1 minus 3. So applying our formula, as always, I had to now square both sides because I want this square root to go out. More like I take the square of both sides, this will cancel out. This is the rule of indices, your fractional power law. So I now have taken the square, I have L1 all over L1 minus 3. Then I simplified using my calculator. And when I simplified, I had this very value. Then I'm left with L1 all over L1 minus 3. Now, men and brethren, I cross multiplied. Let me make that statement here. So cross multiply. So when I cross multiplied, I have this multiply L1 times 1 will give me L1. So now I have this very variable multiplying this whole thing here. That's why I had to introduce my brackets. So 1.573 multiplied by L1 will give me 1.573 L1. Then this multiplied by this will give us this. I collected like terms. Let Lillian meet Lillian. Right? So L1, L1, they went to meet themselves so that they can gossip. Now, after meeting each other, there was a subtraction that happened here, and it gave us this particular value, right? Then this one has negative as well. Yes, negative can cancel negative, or you can multiply through by -1. Then I divided both sides by 0.573. Divide both sides by the coefficient of L1, right? We now got that L1 is equal to what you can see right there on the screen. But what we are asked to find is the length of the new pendulum, which is our L2. So I now did that. Remember that L2 is equal to L1 minus 3. So therefore, L2 is equal to 8.236 minus 3. And then L2 is equal to 5.2632. And that happens to be our option number A. So can this thing reduce now? So can I have the thumbs up? If you are still confused, give me a thumbs down now. Let me see the number of thumbs down I still have. Number of thumbs down I still have. Okay, thumbs down has reduced. Or give me a thumbs up now if you understood what we just did. Good. Only Chin also. Yeah, and Meso good to go. Paul good to go. Lillian good to go. Nobody else. Nikki Good Silva, you're not good to go. Okay. Okay, I have to call your name before you give me thumbs up. Rachel, I know you might not be good to go because you just joined now, right? You left and I think it's your network or your internet. Titi Lola, are we good to go? Okay, Titi is at grandma's place. Maybe she will join us later. All right, so that's your option A for that very particular question that we solved. Remember what I said right here? This dog, you don't chop today. Is to note that it is you are not feeling so well. Oh, so sorry, so sorry. Take a break from that business so you can rest a bit. I know if someone says you should come and deliver now, that sickness will go. If they say they want two delivery now, Piam, you are up and running. Nick, is that also? So note by 2 pi. Note by 2 pi and g are constants. You are healed. I know it's the stress of the whole preparation, right? You know, there's this video that's trending now. You will not die, okay? They say that at some point it will be as if you are going to faint, but you're not going to faint, okay? Oh, that video is very funny. Just manage. You will not die, okay? All right. So that's the first one, right? We're done with the simple pendulum question, and we'll have that very answer. So, Rachel, so sorry about that. Maybe when you get the recording, you can recap so that we can go to the other things. Now, the next one says, if the length of a simple pendulum, yeah, thank you, understanding students. Now, if the length of a simple pendulum is 120 centimeter, calculate its frequency. Did you see what happened there? They said if the length of a simple pendulum, can you see that question? Should I zoom in? For some of you that can't see. Everybody can see it, but everyone can see it. All right, thank you. So now, if the length of a simple pendulum is 120 centimeter, calculate its frequency. They've given us the variable we need, which is pi and g. Remember that your formula for your simple pendulum is t. Are you seeing how that thing is coming at every point in time? Equal to 2 pi, right? Square root of L over G. But what did they ask us to find? They asked us to find what? The frequencies. And also, the frequency is what we're expected to find. But now we can only get the period. And then when we get the period, we now get our frequencies. And also, now, also recall that our frequency is equal to 1 over t. Men are brethren, isn't it? Isn't it? All right. So now f equal to 1 over t. So let's plug in the values. So we have that the values given, we have that your pi, they gave us to be equal to 22 over 7. They gave us g, or you can see it right there. There's no need repeating those things. They gave us that L is equal to 120 centimeter. So that is where it gets tricky. You're not expected to use that 120 centimeter because this one is a meter, right? So you have to convert from centimeter to meter. So you have that L. I'm converting from centimeter to meter. You means you're dividing it by 100. When you divide it by 100, this is equal to what? 1.2 meter. Is that okay, guys? So with that, we can now go ahead to plug in the whole stuff inside the equation, right? we have that T is equal to 2 pi, right? Open brackets. They've given us the value of pi already, which is 22/7. I will still following, guys. So I have 2 times 22/7, then square root of L over G. So L is 1.2, G is 10. So let's go ahead and find the value of our period. So I'm using my calculator. So I have that 2 times 22/7. That will give me 6.286. So this is, 6.286 in 3 decimal place, multiply by, I'm multiplying by square root of 1.2 all over 10. Then any value it gives me, that is my period. And from there, I can now calculate my frequency. So this means that T is equal to, I'm using my calculator. You can be confirming with your own calculator if you have a good calculator, right? So times, I know the one you should be practicing with is that supermarket own, right? So divided by 10. So this will give us that the period is equal to 2.177 seconds. Now, the frequency is what we're asked to find. So the frequency will be equal to 1 all over what? 2.177. So when I do 1 over that my variable, 177, I should have that my frequency. Men and brethren, are still following, please. I have that frequency is equal to, good, 0.459. I hope my answer is in the option. Okay, they approximated to the nearest number right there. So we have 0.45. So that means if you approximate to the 1 decimal place, so 1 decimal place, you have 0.5 hertz. So now 1 dp equal to 1 decimal place simply means that frequency is equal to 0.5 hertz. Men and brethren, does it make sense? Does it make sense, guys? Good, Meso. How about others? Lillian, good, Paul. Titi Lola, I'm not happy that, are you sure you are following? Yeah, Richard, well done. Who again is on the call? Good. How about Susan? Susan has not been joining lessons. I don't know. I didn't see her in class today. Who am I going to ask? It should be Titi Lola. I should ask and Meso. Where is she? And Ferami as well. Please check up on her, please, brethren. I'm not talking about the guys. I'm talking about the ladies to check up on them, please. All right. And someone is trying to laugh somewhere now. The person is holding himself. Some of these my boys. All right, so let's continue. Now, the next question says, hope you understood this very one and how we got that very answer. So option is option D. Yeah, option D. Now, the next one, which of the following will reduce the frequency of oscillation of a simple pendulum? Which of the following will reduce the frequency of oscillation? I think I explained this thing earlier when I was talking about that. Sorry. Which of the, if I said I'm saying the answer already. So which of the following will reduce the frequency of oscillation of a simple pendulum? The frequency of oscillation. So who is going now? What happens when what can actually affect the frequency of oscillation of a simple pendulum? Anybody? B, someone said Richard said decreasing the length of the spring. Okay, next person, please.
Increasing the length. C.
Increasing the length. Justice is going for C. Okay. Who again? Who again? C. Paul is going for C. Okay. Increasing the length of the spring. Meso is giving a thumbs up. So that means she's going for increasing the length of the spring. Is that all? How about other students? Lillian. Lillian. Okay, so let's explain and see who got the answer correct. All right. So based on that, based on that, remember from the formula we can prove that from the formula and also from the experiment, like I explained to you, right? So I said that t, are you listening now, is equal to 2 pi square root of what? Square root of what? Yeah, someone should. So someone's this thing is on. I don't know who that person is. Please, can you mute yourself, please? Now, what happens at this point? Remember that t is the same thing as 1 over f. Equal to 2 pi. So I will show you this based on the formula, and I will show you that based on this as well. L over G. Now, you can see that they are inversely proportional. They are inversely proportional. Can't you see that? L, since this one is down, this one is up. They are inversely proportional. As you increase the length of this one, right? As you increase the length of this one is reducing. Are you seeing it now? Increase this one and reduce this one. I also explained that using this very diagram, right? That if you reduce the length, if the length is smaller, it means that this guy will dangle so much. If I take this short ball and take it up here, displace it as high as this, and then leave it, it's going to dangle up, down, up very well, like because the rope is short. But if the rope is longer, the dangling will not be much. Remember that frequency is number of oscillations per second. So the number of oscillation is going to reduce. Number of oscillation per second is going to reduce. So which means that the correct answer to that very question is simply that increasing the length of the spring is going to reduce the frequency. And it's very obvious from that very diagram that I gave you. So that diagram is something that should guide you so much that the shorter the length, the more it dangles up, down, up, down. You know, I don't want to say this. That's why we say that short people will always, I'm not trying to body shame anybody, but then have you watched ball before? When you're watching, let me speak in Igbo, then I'll find a way to bring it into Yoruba now, right? No, Hana about like you see, the person is running around. You know, when they are running around, the person now, you understand? So anointed and the red, what it simply means is that when somebody is close to the ground, they say that the person runs around so much. You know, you just see as you are running around like a small boy. You know, like a small ball. You know, so they have that tendency of moving to and fro easily because they are already close to the ground. You know, yeah, something like that. So that's what I'm trying to. So I'm using that illustration for you to understand, like short people like us. You know, I'm short, right? How many persons know I'm short? Am I? Just have you seen me before?
You don't look short from the face.
I don't from the face. Ah, okay. Because of the size of my nose, you are wondering that somebody with that size of nose cannot be that short. I see your calculation. I see what you did there, Justice. Oh, voila. You just did an estimate. All right, that's entirely fine. So, what am I trying to explain right here? I'm trying to say that based on this, that the length, the shorter it is, the more it dangles. Everybody, is that okay now? Right? Is that okay now, everybody? Good, good. So anytime you see that kind of question, always remember that it's going to happen that way because of that. So frequency depends on the length and gravity. Is that okay? Of the ball. Okay. Yeah. All right. So it's going to be what? I'm going to circle this very one. When you increase the length, and I've explained why it is so, right? So the longer the rope, the more the frequency. Let me make that statement, right? The more the length of the rope, the more the length of the string, the lower the oscillations. The shorter the length, the more the oscillation. Now, but there's nothing wrong with. I think there's an advantage of being short. Actually, it's a blessing. It's a very huge blessing. A very huge blessing. Rachel, you're a lady. Don't be giving that surprise emoji. God might be packaging a very brief one for you. Very brief one that will be very good. I will take care of you very well. You never can tell. So don't give the surprise emoji. Now, you never can tell. Very sharp one, very brief one. Like when it
Like,
comes to,
why
you said? When they say you may kiss your bride, they will start looking for chair for him to just accelerate a little bit by maximum height.
I know.
Richard is no longer laughing. Richard, don't mind me. The Lord will grant the desires of your heart according to his wishes in glory. If you believe that, can you give me a love emoji now? All right, so that's for the length. Anointed, sorry, Anointed said his battery is going off. Sorry, Anointed. Just do well to charge it, okay? The video is recorded, the class is recorded. All right, now another concept I need to introduce right here, everybody. Please pay attention. There's a concept right here I need to introduce. Okay, now I want to talk about the energy. Please pay attention to this because before I answer that question, there's something I need to talk about. Now, observe this. When you have your simple pendulum, right? Observe that it goes up and comes down. Is that also up, down, up, down? I'm talking about the spring now, the mass on the spring. Is that also? It goes up, down, up, down, up, down. Is that also? Give me a thumbs up if you draw the mass. Like, let me get that image again so that it will make more sense to us. I hope Rachel is not angry with me. Huh? Because I know if her mic was on when I said that thing, she must have said back to sender. If her mic was on, she must have said back to sender, all right. That's entirely fine. Okay, observe this. Let me move it to the right-hand side. Life is good. All right, guys, I think it's okay here for me to make my emphasis. So what am I trying to say about energy when it comes to simple pendulum? Now, if I draw this guy down, it goes up, down, up, down. That's the movement. That's the periodic motion, up, down. You realize that when it gets to that maximum, that up, the velocity is 0. Then it bounces back again. Is that also up, down, up, down? Then as it's coming down, it's going to have more speed here. The speed increases as it's coming down. So that's why, because of that speed, it's going to go down, then still go up again, just that way. But when it comes at this extreme end, the velocities there are 0. Oh God, I don't know. Does it make sense? Like, based on that experiment, good. Based on that experiment, any other person, anyone confused, that's what I'm saying. It goes up here. That's where it stops. Comes down, goes up again. Because as it's coming down, the velocity is increasing because it is going downwards. Do you understand now? It is going what? It's going what? Downwards. Right? And gravity is trying to pull the whole thing down. So it's going to what? Have more speed as it's coming down. So at the maximum, velocity there is 0. At the top here, at the extreme point, what I'm trying to say, based on this diagram here, at the extreme point here, velocity is 0. At the extreme points, up, down, 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 0. But from that mean position, that fixed position we talked about, which is the equilibrium position or the rest position, velocity there is going to be at maximum. Now remember that kinetic energy, Ke, is equal to half mv squared. Now, at extreme positions, we have that V is equal to 0. So that means that kinetic energy at those extreme 1 over 2 mass times 0. So kinetic energy is equal to 0. So what am I trying to say? Right? I'm trying to say that now your energy conservation, energy in simple harmonic motion, which I didn't explain earlier because I felt I was giving a lot of concepts. Now, at extreme positions, like at the extreme positions, are we together now? At the extreme position, kinetic energy, right? At extreme position, at extreme positions, kinetic energy is equal to 0. Are we together? A thumbs up if you understand what I said. Because at that extreme position, the velocity is also equal to 0 because when it gets to that point, it stops moving. Are you there now? At this point, it stops moving. When it gets to this point, it can't move past this point when you actually displace it. It gets to a particular point, that's the maximum displacement. It stops there. Then it comes back to the center, moves to the extreme, comes back to the center, moves to the extreme. So you can't move past that place. So at that point, velocity here is 0. Velocity here at the extreme is 0. But when it comes, as it leaves that extreme point and it's coming down, the gravity is acting upon it and the speed increases as it's coming down. So here, kinetic energy is maximum at the what do you call it? At the equilibrium position. Is that okay? So kinetic energy at extreme position, kinetic energy is equal to 0. Now at equilibrium position, which is at rest, that center, at equilibrium position, in bracket, the center, kinetic energy is maximum. Rachel and Co, do you guys understand? The sisters in the house, do you understand? Sisters in the house, do you understand? Now, what happens right there? If kinetic energy is 0 at that point, it means that at that extreme, that's where we have the highest kinetic energy, highest potential energy. Because at this point, let's check at the top of here. Let me use spring balance now, the mass on the spring. At that top part, the height is the height has increased. Remember that potential energy is what? mgh, which means the more the height, the more the potential energy, right? So at that very extreme point, it has more height, it has more displacement, and hence the potential energy has increased. So potential energy is what? Is maximum at what? At the extreme positions, and is minimum at the center. Does it make sense, guys? So at the lowest point, potential energy is what? Is minimum, and then is maximum. Potential is maximum at those extreme points. Now, you know that potential energy is equal to half mgh. At maximum displacements, I'm coming, guys. At maximum displacement, all right, at maximum displacement, we have that h is equal to the amplitude. And remember that potential energy is a function of height, right? Note that PE is a function of height. Is a function of displacement or height. So what does that mean? Therefore, potential energy, PE, is maximum at extreme position. And minimum at the center. That's equilibrium position. My people, Oti clever. All right. So you left your Igbo, now you're hearing Yoruba. Maybe you have plans. I see. Do you have plans like me? Okay. All right. So any question on this? Any question on this? Okay. If it's clear, everybody, a thumbs up from everybody if it's clear. Lillian and co. All right. So that said, what will be our answer now? What will be our answer from this very question? From what I explained, what will be the answer to that question? Yeah. A, Q. Yeah. Yeah. All right. Next one. Can I continue? Next one. Before this next one, there's a formula we need to introduce here for angular speed. I think this is better this way. If I gave you guys all those equations at the same time, some person must have left this class for me. That's why he's laughing. Let's look at relationship between linear velocity and angular velocity. Between linear velocity, you know the linear velocity v now, right? Velocity. All right. Now, the relationship between those two guys is that V is equal to this omega. People of God, is that clear? Okay, now I remember how that video, they will now start. Is that clear? Come on, Nigeria. All right, so V is equal to R. You will not die, is that clear? So V is equal to R times your what? Omega, right? Now, this is for what? For circular motion. Now, for simple harmonic motion, more like your oscillatory motion, we have that your velocity V is equal to omega square root of a squared minus x squared. Formula be like They like Catholic, you full everywhere.
All these formulas, I tire.
But it's easy now. Look at why I said it's easy. If you can remember that this one, I want to get a justice. If you can remember that this one, V is equal to R is the radius, W is the omega. Now, in place of the radius, because you are dealing with displacement, remember this thing I explained to you back then. Remember this. This is a distance. This is the displacement. So from here to here, the maximum displacement is A. But I told you at every point in time, you are displacing something. From here to here, X. From here to here, X. So you get to the maximum. Do you understand? But if you're moving in a circular motion has to do with from this point, that's the what? The radius. Do you guess? But this time around, this one has to do with your what? Your displacement. Distance from the equilibrium position to what? To the point of suspension. Do you get the point now? So remember that here, R is the radius. The radius of the path. Of the circular path. Are you seeing it now? But for circular motion, sorry. But for oscillatory motion, example, SHM, simple harmonic motion, we have that R is equal to what? That A. Are we together now? Now, just that it is squared. When you start looking for, it has to come from Pythagoras theorem, actually, right? So that's the concept right there for you to actually take note of. So there's nothing you're cramming. Sorry, I'm trying to push fuel into my stomach so that there will be enough energy to drive for a long time. So now this is your circular motion. Then this is your for oscillatory motion. Before they say one young man died while teaching UTME students. So now we have oscillatory motion right here. So that said, A is the maximum displacement, right? And this is X. Now, at X equal to 0, that means at equilibrium position. Take note. Note by at X equals 0. You know, equal 0 means no displacement. Is that also? That's our what? Equilibrium position. We have that V is equal to what? W square root of what? A squared. But remember now, square will cancel that square root. So this will cancel out. So at equilibrium position, you have that V is equal to omega A. Right? So at this point, velocity is maximum at this point. So let's just leave it like this. Like this occurs, that is, velocity is maximum. At equilibrium position, and that's why kinetic energy is also maximum here. If you understood what I just did now, can you give me a thumbs up? Are we confused? Are we confused? Remember that at X equals 0 means that the body is not moving now. Like there's no displacement yet. Observe this. When the object is here, it means there's no displacement. It's just standing right here. Nothing has moved. Do you understand? It's just right here. All right. So at that point, X is equal to 0. And that is where velocity is the highest, because at that point in time, V is equal to omega A. And A is the maximum displacement. And at that point, kinetic energy is maximum. Just to support what I said earlier. Right? Are we all on the same page? Now, can we go ahead and solve that very problem that they gave us here? So they said, from the question, they said that angular speed of an object describes a circle of radius 4 meters with linear constant speed 10 meters per second. Now, what does that tell you? It simply means that, are we together? That for that place, R is equal to 4m, V is equal to what? 10 meter per second. Then they are asking us about our what? Our omega. I had to just relate that so that in case I see something similar to that we're going to solve. So for the question given, we have that V is equal to R omega. So that V, what's the value of V? People of God, are we following, guys? If you're following, can you give me a thumbs up, please? All right. So from that question, we'll have that V is 10 meter per second, R is equal to 4 meter. So that means 10 is equal to 4 omega. So which means that omega is equal to 10. Sorry. Yes, is equal to 10 over 4. All right. So that said, this implies that omega 10 over 4 will give us 2.5 rad seconds. Any question, guys? So we've actually tackled that very problem. So W equal to this. Now, the next problem we have right here is this one. And I think we can answer that very question. Let me zoom on it. It said, if a freely suspended object is pulled to one side and released, it oscillates about the point of suspension because of what? Let me see your answers. I've explained that during the course of the lessons since last week. If a freely suspended object is pulled to one side and released, it oscillates about the point of suspension because of what? Let me see your answers on the chart. Any idea? Anybody saying anything? A. Who again is saying A? Let me check the charts. Okay, Emmanuel said A. Chinonsoya. Paul said A. Okay, interesting. How about if the ladies? Anyone? Justice said B. Okay. Who again? Justice is standing for B. Who again? Who again? Lillian and Co. What's your answer? Lillian, Metsoma, what's your answer based on what we've been doing so far? Titilola and the rest of them. What? A. Mesa said A. Okay. So let's analyze it. The answer is just there looking at us. There's nothing to even analyze, right? I said that the acceleration is usually directly proportional to the displacement. The more the displacement, now, Justice, take notes, please, because you said B. The question says, if a freely suspended object is pulled to one side and released, it oscillates about the point of suspension because of what? It moves up and down because acceleration is directly proportional to the displacement. We've explained this before, right, when we introduced our lessons. Is that okay now? So the more you pull the body, remember I told you something back then. Let's assume that this is the point here. Let's assume this is our spring, and the spring is carrying a body of this very weight. And let's say that we'll draw it downwards, we'll pull it to this point, we'll pull it down. Let's say that this is the equilibrium. Let's say that's at rest here. And then let's say that we'll displace it to a height. Let's say here is Y, that's suspended. Now, the acceleration, because of that pulling, acceleration will be acting the other way around, because when you put the thing down, pull downwards. What happens here is going to do what? Accelerate. Is that not so? You're going to move what? Moves up. Justice, is that clear now? Justice, is that clear now? Justice, is that clear?
Yeah, it's clear. I was not in the last class. That's why.
Oh, okay, no wonder. And you've not watched the record, you just casted yourself now. And you've not watched the recording. That's quite bad. All right. The motion of a simple pendulum. So that means that recap I was doing was just for you. No wonder you're giving me thumbs up to continue doing the recap because you were not in class. I didn't watch the recording. You are using my head. So the motion of a simple pendulum is what? I need your answers in the chat as fast as possible. The motion of a simple pendulum is what? The motion of a simple pendulum is what?
A.
A. Justice said A. Who again? Tin also said A. Okay. Gift said A. Who again? Okay, Rachel said A. All right. Lillian said A. Yeah, it's oscillatory because it's a to and fro motion. Right. It is a to and fro motion. Is that also? It is a to and fro motion, right? So this is true. To and fro motion, right? So it goes up, down, up, down. So this is what? Oscillatory motion. All right. So that said, the next one says a particle vibrated with simple harmonic motion. If the acceleration is 25 times, are you there? 25 times its displacement in meters, find the period of motion in terms of pi, right? Now, this is related to what we also learned the other time. So if a particle vibrated with simple harmonic motion, and they said 25 times its displacement in meters, find the period of motion in this. Now, remember that your acceleration A is directly proportional to your displacement. And from the formula, we said that A is equal to minus W square X. How many of you can still remember that formula? How many of you can still remember that formula? Good. And then they said that the particle with simple harmonic motion, or if the acceleration is 25 times the displacement, are you seeing what they said here? Acceleration is what? 25 times the displacement. Acceleration is 25 times the displacement. So they said that your acceleration, acceleration A, they said is equal to what? 25 times your displacement. Are we together? A is equal to 25. So let me write here, in case when we get the PDF, sometimes it's very, very small when you write on the other side of the paper. So now, remember what I said from the introduction that we did earlier, that we have A will be directly proportional to the displacement. So A, from that formula we had then, x squared r. Now, the question said from what we had that acceleration is 25 times the displacement. So we have that A, they said is 25 times. This is where I'm getting it from. So that A is equal to 25 times displacement x. So it means that, are we together? A is 25. So it means that 25x is equal to minus W squared x. Now, what that implies is that x will cancel x. You know that this negative is just trying to tell us the direction. Is that not so? Negative is just the direction. It doesn't affect our answer. So we have that W, yes, is equal to what? Square root of 25. So that W is equal to what? 5 rad per seconds. Note by the sign simply indicates the direction of acceleration. Are we together? Direction of acceleration. But are we done yet? No, because they said we should find what? The period. Is that also? That's what we are asked to find. The acceleration, sorry, the period in terms of what? Pi. So what else can we do? Remember the relationship between your angular velocity and your period, right? So there's a relationship between them. Remember that your omega is equal to 2 pi all over t. So that t will give us 2 pi divided by m. But remember that we are asked to leave our answer in terms of what? Pi, right? So I have here to be my omega, so that my period t will now be equal to 2 omega divided by what? The radian is 5. And we know that 2 over 5 should give us 0.4. So this is 0.4 pi seconds. So that implies that we've calculated our distance following those formulas we've been practicing all this while. So you can see that the formula revolves around the same place, and there's nothing so much. You see that you are cramming right there. Just few formulas to remember. But that's why outside there is quite easy, right? They give them formula sheets. All you need to remember is how to apply it. All these formulas we are cramming now, they give them a formula sheet that you can simply look up the formula, right? I'm telling you. So all you need to remember is just how to apply the formula. But you know, it is what it is. So now this should be, and also my dear, it is what it is. But that trains you to be intelligent actually. But I don't think so. It's just stress on its own, right? Because you have a lot of things to remember already. So this is our option number D. All right. So the next question, this one says a particle performs simple harmonic motion with an amplitude. Are we there? Hope I'm not. Am I speaking any question? Did I skip any? No. All right. I want to ensure I solve it. Oh more. God. We still have a lot of questions to solve. Well, anyway, I stop. You guys will take over. Now, a particle performs simple harmonic motion with an amplitude of 10 meter. Yeah, I was going through. The question is too much. Those questions you guys are sending on the group. Determine the period. Okay. We've answered this one. So this one says that a particle performs simple harmonic motion with an amplitude of 10 centimeter and a period of 20 meter of 2.0. Sorry. Are we there? Then we are asked to estimate what? Is 6.0. Okay. Do you guys want to try? Or should I go ahead and solve? Should I carry my cross and be going? I carry on, right? Okay, Mesha is giving thumbs up. Young man, carry your cross and keep going. Okay, no problem. Now, a particle performs simple harmonic motion, that's SHM, with an amplitude of what? Of 10 meter, 10 centimeter. So A is equal to 10 centimeter. Our work is to convert to meter. So it means that A is equal to what? 10 over 100. 0 cancel 0. So that A is equal to what? 0.1 meter. We've converted first. Now, the next thing is that on a period of 2.0 seconds, it means that T is equal to what? 2 seconds. What is the magnitude of its acceleration? So acceleration, we do not know. When its displacement from the equilibrium position is 6.0 centimeter, it means that X, are we there? Are we together? We have that X is equal to what? 6.0 centimeter. So X is equal to, I'm going to divide that by 100, right? So 6 divided by 100. So X is equal to what? 0.06 not centimeter again, meter. All right, so let me write by the side because sometimes if I export this, it doesn't really show. So we have that A is equal to what? I've converted 0.1 meter. We'll have that T is equal to what? 2 seconds. We'll have that acceleration is what we seek. We'll have that X is equal to 0.06 meter. Now, what can we use right here? They are looking for the acceleration. So recall, right, that your acceleration is equal to W squared X. Remember that symbol that sign is just to show the direction. Is that not so? Is equal to W squared X. Now, but omega squared rather. But omega is equal to, they gave us the period T is 2 pi all over T. What was given to you requires what you are going to do. So let's go ahead and find the value of omega. So omega is equal to 2 times pi divided by the period is 2. So what does that mean? We're going to be left with only pi. Is that also? Is it pi or pi? Which one? So W, sorry, I keep calling this in. This is omega, please. Is equal to what? Equal to pi. So we're going to go ahead to plug this very value so we can get our acceleration. So because the only thing linking acceleration and displacement is this formula. Always remember this. So therefore, we now have that omega is W over this. Now we can go ahead. Acceleration is equal to omega squared X. Acceleration is equal to omega is pi squared. And our X is, what's the value of X? X is 0 times by what? 0.06. So that acceleration is equal to, where's my calculator? Shift pi squared multiplied by 0.06. So that will give me the acceleration is 0.59 rate per second squared. Or meter, okay, soon you read this, meter per second rather. Meter per second squared. Did I confuse anybody at this point? Did I by chance confuse anybody? Okay, good. So if you are following, can you give me a love emoji? So which means we have our answer right here. Good, thank you. Good. Lydia, I said love emoji. I'll give me a I will fight with you. Thank you, Chin also. All right. Don't worry. So this is our answer right here. Right. So we have our answer to be option D. Sorry, option what did I circle? Option C, right? So this is option C. When I look at the number of questions remaining, I just get tired. So now the next one is that determine the period of oscillation of a body executing simple harmonic motion whose angular velocity. Can we try this one, please? Someone should try this out. They've given you, they're asking for the period of a simple harmonic motion, but they've given you the angular velocity. That's omega. Can someone just try that out, please? Anybody? Did I solve? Or you guys are solving? A thumbs up if you are solving, if you are working on it. A thumbs up if you are working on it. A thumbs down if I should work it. Should I go ahead and work? Or we are trying it out? Nobody is saying anything. Oh, wow. Right. I should solve. Okay, let me go ahead and solve. Later, you can try more questions on your own. So let me see if I will meet up with the number of questions we have right here. So when you are watching the recording, you understand it better, and then you could repeat the solvings. All right. So let's go back again. Now they said I should determine the period of, okay, someone said C. Okay, is that Meso? All right, so let's see. Okay, Meso said C, okay. right. So let's see what happens right here. Now, remember that for this very question, they're asking about the period T is what they're asking us of, right? Now, they give us the omega to be what? 628 rad per second. Now, what's the formula linking the both of them? Is that omega is 2 pi all over T. This is 628 is equal to 2 pi all over T. When you cross multiply, you have 628T is equal to 2 pi. So you now go ahead and divide both sides by 628. So we'll have 628 right here. Then we'll have 628 right here. Now, with that, we can now estimate the period. So here cancels here. So we can now have that T is equal to, where's my calculator? I have 2 shifts pi divided by 628. That'll give me 0.01 seconds. But let's check our options. You can see that the options are in milliseconds. Are you there? The answers are in milliseconds, right? So now, how do we convert milliseconds to seconds? How do we convert milliseconds to seconds? Where are the scientists in the house? Nobody's talking. You don't know the conversion factor. Multiply by what?
1,000.
By 1,000, right? Right, because recall, that's a good one, Meso. So recall that 1 sec is equal to what? 1,000 milliseconds. So that means that 0.01 seconds will be equal to what? 0.01 multiplied by 1,000. Is that also? Milliseconds. So that T will be equal to, that's 10 milliseconds. That's correct. Well done. So our answer here is going to be C, just like Meso already said. You're doing well. So this is what? Option C. All right, so let's go again. The next one says, a body moves in simple harmonic motion between 2 points. Can you see that? A body moves in simple harmonic motion between 2 points, 20 meters on the straight line, joining the points, right? So if I'm to draw this diagram, let's say we have this. This is a straight line. That means it should be more like mass on the spring. So let's have something like this. Then we'll have the spring. Then let's have the mass attached to it this way. Now, so a body moves in simple harmonic motion between 2 points, 20 meters on the straight line, joining the 2 points. All right. So let's say that when we move this up and down, let's have, when I stretch this, it goes up and down. Let's say that the distance between the 2 points, let's say that this is the maximum, this is the minimum, right? So let's say this is point A and this is point B, and the distance joining the 2 points will have 20 meters, right? So if the angular speed of the body is 5 rad per second, so now angular speed omega is equal to 5 rad per second. Calculate the speed when it is 6 meters from the center of motion. Let this place be our center of motion at equilibrium. Are we together now? So we should calculate the speed when it is 6 centimeters from the center of motion. So let's assume that they are saying that at least the distance from here to here, this my diagram might not be really correct, is 6 meters. Now, who can tell me what will be the amplitude of this motion? What will be the amplitude? Let me use different numbering here. how do we calculate the amplitude? If the distance between the 2 points, the extreme points, you know, these are the extreme points. That means when I stretch this thing down, it moves to this point, B, bounces to C, C to B, C to B, and then this is the center point. So what do you think should be the amplitude? So we are looking for the speed. The speed V is unknown. So what will be the amplitude? So recall, since they are talking about simple harmonic motion, that for simple harmonic motion, relationship with speed and angular velocity. That's linear speed / angular velocity. You have that the relationship is that V is equal to omega. That formula I gave us then, V equal to omega square root of A squared minus X squared, right? So now I need to get the amplitude, A. Remember that the amplitude now is going to be the distance from here to here, like the maximum height now is going to be half of it from here towards to this place. Here will be your amplitude. Also from here to here, from the center now to this place will also be your amplitude. Do you understand what I'm saying? If you understand what I say, can you give me a thumbs up? Okay. Let's say you don't understand. Like, okay, sorry. Look at what I'm saying. Remember that for this, let's use this spring now. Let's use a simple pendulum. Remember that your maximum displacement is here. Distance from here to here is maximum displacement. Is that also? This is your maximum displacement, right? Also, from here to here is also your maximum displacement, A. Now, somebody is telling you that the distance between this point here and this point here, that the total distance between here to here is 20 meters. But remember that your maximum displacement is the distance between from the center to that suspension point, center to suspension point. Remember that the maximum displacement will be from here to here. This is your amplitude. This is also your amplitude. But distance between the 2 points is from here to here. Does that make sense? Good. I think this diagram, let's make use of this diagram. Let's make use of this diagram for that question. Thank you for taking me back to that place. I think this diagram will make more sense for that question for you guys to capture what I'm saying. Right. Titi, where did you go this why?
So I had to go drop some things for my sisters.
Okay. Oh, family man. Yeah, doing well. What did I do? Man, I was saying family man, I was cleaning what I needed. Okay. I said let me change the distance. We should hold Paul responsible for that. All right, so let's go. Look at what I'm saying. Miss, thank you for that question. That will make me think out of the box now to explain better for you. So let's use this now. This will make more sense. So they said that let's use this diagram for it. Are you there? Let's make use of this diagram for it. Let me zoom it up a bit so it makes more sense. Let me zoom it up a bit. Good. Let me move it up. Good. So assuming that this is the diagram now, right? So let this be my point C. This is the point they're talking about. A body moves in simple harmonic motion between 2 points. Let's call this point C and let's call this point D. Now, if the angular speed of the body is 5 rad per second, so angular speed is 5 rad per second. Right? Then they are saying they're asking us to calculate the speed when it is 5 meters from the center. Let's assume that the distance, this is the center. This is the center. So let's say that the distance from that center is 5 meters. We should calculate it when it is 5 meters, 6 meters from the center. So from here to here, let's assume that the distance from here to here is your 6 meters. Do you understand it now? But remember that the distance from here to here, that's the distance from here to here, from here, I want to use a different colors that will come out very well, that will make emphasis on that. Remember that from here, the whole of here, from here to here, is going to be your amplitude A. Now, but they said that the distance between the 2 points, from point C to point D, they said that that distance is 20 meters. So measure from what I explained now, what will be the value of the amplitude, you and Lillian? What will be the value of amplitude? If you understood what I said, what will not be the value of the amplitude? Good. Titi, God bless you. So now, the amplitude will now be equal to what? 20 divided by 2, which is equal to what? 10 what? 10 meter. Because I have distance between the 2 points. Then the amplitude, are you getting it now? Remember that this is your what? Amplitude. So what's happening? Miss, are you still confused? Please turn on your mic. Let me know what the challenge is, please. You just clicked. Okay. Lillian, are you still confused? Lillian, still confused? Yeah, open up now. Open up if you are still confused, right? So distance between 2 points from here to here is 20 meters. That's what they said. But your amplitude is the maximum displacement. The object cannot move past this place. This is the highest place it can stay. So the distance from the center to that highest place it can stay is what we regard as the amplitude. But the distance between the 2 points where the object is going to move, I wish I know how to. There's no way I can animate this now. I cannot. I'm not a miracle worker. I wish you have a technology. Yeah, there are some technologies outside there that will animate this ball. You see this center ball now moving from here back to the center, back to this place. But since we don't have it. Oh yeah, use imagination. Imagination go wound you for this class. So use imagination now. Imagine this ball now moving. This is the center position. It moves from here to C. From C, it moves back to D. So distance between moving from C back to D is 20 meters. But the maximum displacement is what? From the center back to D. Or from the center back to C. Yeah, you can use AI, but how do you start using that inside the class now? There's no time now. So you can actually animate. It moves from here to this point, then from here down to the other point. So observe that movement. Observe. But I think even what I'm saying now, you can imagine it. Is that okay? Everybody now, is that okay? Yeah, thank you, Paul. Who again? Who again is giving me a thumbs up? Lillian, are you still confused? I'm more confused. Lillian was the person that said she's not following. Lillian, are you following now? Susan and Ferami, you guys came late to class, so there's nothing I can do about it. Justice, are you following? All right. So that said, I can plug in my values now, right? Remember that they are looking for the velocity at the point x equal to 6, right? So we have our amplitude. Now we have that x is equal to 6 meters. So right here, we have that A will be equal to the amplitude is what I have this guy, the omega. Omega is 5 rad. So I have 5 right here. Sorry. This one is 10 meters. So my x is 6 meters. Right. So omega is equal to 5 rad per second. So let's go ahead and get the velocity at that point. So my v will be equal to 5 square root of 10 squared minus by 6 squared. So v equal to 5 times 10 squared minus 6 squared. That's 5 root 64. Is that also? 100 minus 36, 64. So that will give us 5 times 8. So that V is equal to 5 by 8. That will give us 40 mangoes, right? So what's the unit? 40 meter per second. So we're going to have 40 meter per second. So that means we have our answer right here. Yeah, do you understand? People that came to class on time, do you understand? Everyone? All right. I think the other persons, they're going to watch the class recording. So we can save time. So this is C. This is option C. But just stay in the class so that as you're watching the video, remember that, yeah, these were the few things I said. Option C. All right. Yay. Yay. This question, no, they finish. Now, which of the following with respect to a body performing simple harmonic motion are in phase? Right? Okay, happening in phase, like they are the same. Like, so for them to be in phase, actually, is this one. A very brief explanation is force and acceleration. They are in phase, actually, right? Because they act in the same direction. So if I'm to answer that question properly, the force are in phase. But because I want to give you additional stuff on this, let me tell you a few things about that, right? So for phase relationship, understand this phase relationship, that displacement and velocity are the phase relationship. Let's look at the phase relationships, right? If you can remember, it's good and fine. If you cannot, that's entirely fine as well. But just remember that when it comes to simple harmonic motion, you can only talk about force and the acceleration, right? Because both of them are acting at the center, that's at the equilibrium position. So for this one, they are 90 degrees out of phase. There are some derivations to this, but I don't think it's important at this point. So the phase relationship is that these ones are 90 degrees out of phase. Now, velocity and acceleration, are you there? Velocity and acceleration, they are 90 degrees out of phase as well. Right. Now, displacement and velocity and acceleration, right? Then force acting on the body, right? These ones are in phase, right? Are in phase, right? And because of what? Both of them act in the same direction. And it's always towards the center. Towards the center. In brackets, the equilibrium position. All right, so that's for that. For simple harmonic motion, you have to always relate it to your force and their acceleration. Is that okay? So how many questions are remaining here? 1, 2, 3, 4, 5, 6, 7 questions. So I will solve one more and then the rest will go to you guys. The motion, okay, this one is not calculation. So which of the motion above is simple harmonic? Everybody now, your answers should roll in. Which of the following is simple harmonic? So what do we have? Okay, let me look at the chart. Okay, Measure said B, and B is motion of a loaded test tube. I, the beating of the heart, and V the motion of pistons in a gasoline. Titi said C. C says motion of loaded tube. I agree with motion of loaded tube. I, the beating of a heart. IV. So why changing your answer? You are correct now. B is correct because why is B correct? Now look at this. Yeah, B is correct, Mason. You are changing it. You are changing to C because your other ladies are saying C. Susan, Ferami, and Titi is
No,
saying
I'm
C.
not sure of
Look at
that.
it. The
Motion of piston is confusing.
okay, the beating of the heart, the beating of the heart. People should know that beating of the heart is simple harmony. It goes up, pim, like to and fro. Especially when you went to commit a crime, or you've spoiled something, and they are asking who spoiled it. At that point, you don't know what to say. So that motion is, and you'll be sweating profusely. I don't know. There's one. Let me share this story. There's one particular day, man. They gave me the key to open the door. No, what happened that day was like, I think they asked someone, either my elder sister or my elder, to go and open the door or something. Then I quickly collected the key from them. You know that all those young people, how funny we can be. Then I'm brethren. I inserted the key into the door, but the thing broke inside. Just dismissed. So I didn't know what to do. Like everybody was still outside. Like I was just sweating from nowhere. Like how will you, But funny enough, that day, I think what happened is that sometimes when you feel that a lot will happen, that day nothing will happen even. So when they just came, my dad was like, "Oh, that door has been giving sign all this while." I say, "God, now show your hand there." He said that the door has been disturbing, so that he finally spoils today. I said something I was thinking how to cook one or two. You know how you can manufacture lies within 2 seconds like this. All right. So the beating of the heart is a to and fro motion. So it's oscillatory motion. Now, a stone tied to string and wheeled round. No, that one is circular motion. Right. So this one is circular motion. Yeah, this is oscillatory. We agree. Here, this is circular because you are turning it around, right? Motion of piston rings go up. It goes up and down. You're not a driver. That's why you don't know about it. You're not a mechanical engineer. All you care about is to sit. All you care about to mess up is to sit in front of the car now. Abi? All right. So this one is actually oscillatory. Whatever happens in the engine, that's not your business. All right. So the answer is a B. Right. Susan and Titilola, have you seen why it is B, right? So, men and brethren, I think at this point we'll take a bow so that you can prep for your biology class. So, I left how many questions for you? 1, 2, 1, 2, 3, 4, 4, 5, 6. That's why I say come to class on time. I came here around 10 o'clock, right? I waited till like 10:05. So, do what always. If you guys came to class on time, I should have finished this, right? But you guys don't come to class on time. And I wish us all the best. I think I've solved most of the questions. How many questions did I solve today? This is 1, 2, 3, 4, 5, 6, 7, 8, 9, my God, 10, 11, 12, 13, 14. So I think I deserve a love emoji, guys. I think I deserve that. I think I end it today. Yeah. Thank you, everyone. Thank you, Ferrami. Thank you, Meso. Thank you, Paul. Thank you, Justice. Justice will always give me a thumbs up when others are sending love emoji. All right. So that's for that, everyone. So I will see us on, I think, I think this is the last physics class for the week, right? That's the last physics class for the week. Yeah, that's the last physics class for the week. All right. So for the maths guys, I will see us tomorrow. I wanted to fix another class for physics on Friday, but I'm owing the maths guys a class, and that should happen on Friday by the mercies of God. So all the best. I'm sending the slide to the class. So do well to look at it and solve the remaining questions and send the questions to my DM. And you have your video lessons for the week. about 5 videos to catch up so we can cover the topics, right? So in our next class, I'll be looking at equilibrium of forces. I'm glad we're making progress, and I wish us all the best. I'm rooting for you all. And remember that on Sunday will be our family time where we discuss to know the challenges we are facing so far, get to know ourselves better, and see how we can assist each other. So please, that day, I don't want to hear I'm in a place I cannot turn on my mic. Please find a good spot, a place you can talk, a place you can laugh, a place you can be free to share whatever thing you're going through. It's going to be a beautiful session that very Sunday. So we'll get to know ourselves better and walk the journey together. All the best, guys. I love you all, and I pray that our effort is going to pay off. Thank you. Remember your class. I think your biology class at 12:30 p.m. All the best, guys.